Okay, good morning, everyone. Welcome to day 2 of the workshop. Our first speaker today is going to be Johannes Buchner. He's from MPE in Germany. He's the author of the Bayesian X-ray analysis software, which if you're unfamiliar with now, you're going to be an expert in by the end of the week. So he's going to give us a quick tour of this package and the methods behind it. So Johannes, take it away.
Thank you. Good morning, everyone. I just want first to ask people online whether they can hear me okay, because I'm using my laptop microphone.
It's okay, thank you.
Yep, all good. All right, so welcome. I will try to introduce some concepts today about Bayesian X-ray spectral analysis. And it's a language that all fields of astronomy use, so you'll be able to talk to other people as well, not just within X-ray astronomy. The practical aspects of how to use the package will come later in the tutorial. And sort of half of this talk is things you shouldn't be doing and why. And then the later bit is things that I found to work and might be useful to you as well. Okay, so I will be introducing Bayesian inference, how to constrain parameters, what algorithms exist for exploring parameter spaces, in particular nested sampling, which you probably are unfamiliar with, how to do model comparison reliably. I probably won't have time to talk about how to combine information from many sources, for example, how to make sample distributions. Maybe I'll be able to cover it on another day, and how to model backgrounds. So let's get started. We already introduced sort of the story. We tell ourselves how our detectors receive the photon counts, and that story is you have some source, let's say it's a point source, you receive an X-ray flux from that, your telescope and detector picks that up. We model that with a linear algebra response. So we multiply this with a matrix, and maybe we have some additional background. And finally, we get the counts, the number of counts we expect in each detector channel. So this is an expected number of counts. Maybe you have 3.2 counts expected. And then you try to compare that to the actual number of counts, which is an integer. Maybe it's 5, and then you ask, well, is this under Poisson probabilities? Is that a reasonable result? And then you vary your model most of the time here to see what models are reasonable. Here's an image of one of those responses from RxT. We already said it's not diagonal, it's not invertible, so that's why we do forward fold. Then already was introduced 2 assumptions on how you can model the data that you receive. In other fields, it's common to use a Gaussian likelihood. Here's the formula. You know this. Then if you apply this magical trick of taking the log of this and multiplying it with -2, you get this on the bottom right, and that's what people call chi-square. Sum this up over many data points. We don't have Gaussian data, we have Poisson data, so let's do the same thing. On the top right, you have the formula for Poisson. You can take the log and multiply by -2, then you get something, and that's what people call, depending on what constants you drop here, hash or c-stat statistics. Now, just because something's called chi-square or something like that doesn't mean it actually follows chi-square distributions. So you might want to verify how this thing behaves. But okay, just want to introduce you to, we are doing Poisson likelihoods. We just call it in a certain way. But if you want to talk to other people, say I'm using a Poisson likelihood. Okay, so how do we do inference with these likelihoods? So you have some likelihood, which is a function which tells you, given your data and given all your model assumptions, your model parameters, your response, your background, and so forth, given all of this, you get a value out. Okay, and higher likelihood generally means this model under these assumptions frequently produces data like this. If you have lower likelihood, this model less frequently produces this data. Okay? So it's a function. It tells you the frequency of data. It's not, by itself, it's not a probability distribution over these parameters. It's just a function. Okay, so you already experimented in the tutorials with making best fits and doing sort of some error estimates. So briefly, let me talk about how that works. So you use the minimizer, find the best fit. And now the question is, how do you get errors, right? Now you only have a function, you can walk around and evaluate that function. Now, what are confidence intervals? And I'm in favor of using the right thing for the right question. So I will just explain to you what confidence intervals are, how they work, when you ask yourself whether this is something you want to do. So if you find the best fit in your data, you assume those parameters. Now you generate many data sets. Let's say you generate 100 data sets, assuming that best fit value. And now you find the best fit for all of these data sets. And in each of those data sets, you walk down -1 in the C-stat. That gives you a range on that parameter. And then in 68% of those cases, that range contains the assumed parameter. That's the definition of a confidence interval. So what was the question again? What we wanted to do? Actually, we wanted to know what's the true parameter. But we assumed the best fit is the true parameter and made something with it. So also this going down -1 in log likelihood, that assumes a bunch of things. The assumptions are written here. There are 4 assumptions. One is you have to be away from the boundaries of the parameter space. It doesn't work if you're limited to 0, for example, and above, but you are actually close to that border. You also have to assume that your model is linear in its parameters. That's basically never the case. Third, you have to have a high number of data so that your likelihood looks like this Gaussian. When is that the case? And finally, you're assuming that your best fit is the true input, right? Because that's what you use to make all of these instances. Okay, then you can do this. Okay, so that's one thing. The other thing is what you do then with these confidence intervals. Let's say you have 10 sources, and now you want to know, well, how is that parameter distributed? What's, for example, the temperature or luminosity distribution? Now, if for each object you have some C-stat or likelihood contours like this, how do you combine them to get a sample distribution? Of course, you can take the best fit and make a histogram of these best fits, or a cumulative histogram. But now you're not taking into account that these error bars are different between those sources. So what does that really mean? You're sort of mixing the uncertainties, the measurement with the sample distribution. There's a very nice way of going about this with hierarchical Bayesian models that will come up later in the week. Okay, so what do we actually want to do? What we want is we want to make some statements about some parameter, luminosity or temperature, for example. We want to say, well, within it's within some range with some probability. So we want to say, okay, the temperature is between, I don't know, 10,000 Kelvin and 20,000 Kelvin with 90% probability. Okay. So that's a probability density that we're defining. Probability distribution over that parameter. And this has also the property that if you consider infinitely small region of that parameter range, there's no probability in there. So between 10,000 Kelvin and 10,000.0001 Kelvin, there's basically no probability because the range is so narrow. Okay. So you have this probability density, and it's associated with some volume that you're integrating. And that gives a probability, it's called a probability mass. And what we want to do is find the regions in this parameter space that contains most of this probability mass. Okay? So we try to find regions with high probability mass, and that's what we use certain algorithms for. What we have are these likelihoods, this probability of the data given our assumptions. And there is no method that produces what we want just from likelihoods. But we have the next best thing, which is Bayesian inference. So let me come to that. And Bayesian inference is based on the theorem of conditional probability. So here's a Venn diagram. You have some event B and some event A, and you're asking what's the probability for both of them occurring. So you can come from the right side, you say, okay, you have the probability for B occurring, and then you ask, well, what's the part in green here? Well, it's the probability of A occurring, given that you're already in B. That's how you use this. But you can also come from the left side and say, okay, it's the probability of A occurring, multiplied, that means both have to be true, probability of A occurring times probability of B occurring, given that you already know that you're in B. Okay, and those have to be equal. You rearrange them a bit, and now you interpret A and B in terms of data and parameters. And then you're at a Bayes theorem. That's what's written here. On the left is what we're actually interested in, this probability distribution over the parameter space given our data. On the top right, you have the likelihood function. This is something we have. But as I said, on the top right, it's a function. On the left, we have a density that we can integrate. So how does that work? Well, we have to start with a density. And that's the prior that gives us that. So you start with a prior probability density, you weigh it sort of with this likelihood, and then you get an update, which is the posterior. On the bottom is a normalizing factor, which is called the evidence. It's sort of the average likelihood over the parameter space. So you can just integrate the top part to get this normalizing. So you integrate the likelihood over the parameter space. And how do you decide which regions to make large and small? How do you define how to integrate? Well, that's the prior. Okay, so now we have our probability distribution over some parameter. And we want to find where most of this probability is. And because parameter spaces can often be very large, it doesn't really make sense, or you have to find a way to describe this probability distribution. And very often we do this with samples from this parameter space, which means basically a list of coordinates in this parameter space. And it's assumed that each of those coordinates are equally probable. But if you make a histogram, you sort of get this probability distribution out. So like shown here, you have these samples of the posterior. If you make a histogram, you approximate that. And it's quite convenient to work with these samples. How do you generate them? Well, simplistically, you could evaluate over a grid and then weigh and draw randomly based on the weight. Okay, so how do you use these posterior samples or posterior chains? Well, if you, for example, take just the first coordinate of each of those samples, then you can make a histogram. You can find the quantiles that tells you where most of the probability is. So between the 10% and the 90% quantile is 80% of the probability of this distribution. Or you can ask, well, how much probability is above some value? You just count what fraction of samples are above that. And so you can ask interesting questions using those samples. And you can also take each of those samples and compute something else. You apply a function to it, and then you get a distribution in that different space. And that's a very nice way of propagating uncertainties. For example, here I computed for each sample a model, and here I'm showing the distribution of these model predictions. Okay, so how do we actually go about computing things like that? As I said, we produce grids. So here is a two-dimensional parameter space. You make a grid. Let's make it uniform, and you evaluate the likelihood everywhere. And then you ask, well, where is most of this probability ending up? So you could identify the region here that contains 90% of the probability. You can also compute the evidence by taking the average of these likelihood. Okay, fine. But now what happens if you take your model and you reparameterize it? Let's say, for example, you have let's say, exponential cutoff. Now, instead of writing theta for that, you write log theta in that form. Now, if you make a uniform gridding in that changed parameter, suddenly you're getting something different if you look at it in this space, right? Suddenly you get something like this. And so just by changing the parameterization, equal spaced or uniform means something different. There's not a unique definition of what is equally distributed. And that's exactly this sort of spacing, how you choose this, how you choose what is the natural space to integrate in. That's what the prior does. So just be aware of that. Now I want to briefly talk about Bayesian model comparison because it's basically the same idea. You have two models here, model 2, model 1. You put grid points in each, and you ask, well, where is 90% of my probability? Maybe 90% of the probability is in model 2. And then you can say, well, model 1 is not very important, apparently. And so this is one way to do model comparison with base factors. So you take the average likelihood of model 1 divided by the average likelihood of model 2. But again, you have an additional question. How many points do you put in model 1 and how many points do you put in model 2? And that's the prior on which model you prefer to priority. Okay? And that doesn't have to be necessarily equal. Okay, so grids are nice, but they don't work well, especially if you have more than 3 parameters. So you can easily see that by saying, okay, you have 10 grid points in each dimension. If you have 3 parameters, you already need 1,000 points to evaluate that grid. If you have 10 parameters, you need 10 to the 10. You will have an issue representing that on the computer. So in practice, we use some techniques. I will briefly go through them to do not something like that, but to sample stochastically from this parameter space. And these techniques produce samples, again, these coordinates in this parameter space that represent the posterior. They can be just the coordinates or with weights in the first technique that I'm showing. So important sampling, nobody does this in X-ray astronomy, but just for completeness, the idea here is that you use an auxiliary function, the one in red here, which looks very similar to your posterior, if you don't know yet. But let's say you have this proposal distribution, you can draw some samples from that, and then you compare the ratio of your posterior to what your proposal density is. So you're sort of trying to find this correction factor by which your proposal distribution is off, and downweight samples that you drew too often. And that's can be efficient, especially in lower dimensions. It's easy to parallelize because you're just drawing samples and evaluate them. And you can do integrals, but it really is reliant on getting a good guess of this proposal distribution. And it also doesn't work very well for high dimension. But you can also in BXA, you can get out the prior and the likelihood, and then apply a sample like this to your problem. Much more popular is Markov chain Monte Carlo, so let me talk about that for a little while. The idea here is that you have a walker which jumps around in this parameter space. So on the top right, you have your walker. It has a proposal distribution which tells it where to go next. So it tries out randomly a step, and at that step it looks if your posterior is higher or lower. If it is higher, it would always go there. If it is much lower, it would not go there, it would just stay where it is. And if it's a little bit lower, it goes there with probability that's proportional to how much worse that fit is. So you need this, this proposal distribution. It's also called a transition kernel. It defines how you would walk around in this space. It produces a chain of visited points, and that chain is, the idea is that that chain is proportional ultimately to your posterior distribution. Okay, and there are many transition kernels that have been defined. The simplest one is this random walk with the Gaussian. It takes very long to explore parameter spaces, especially in higher dimensions. There's another, well, there's this technique called affine invariant ensemble, Markov chain Monte Carlo. That is has been published by Buchner and Weir, and it's implemented in the popular package MC. It's sort of part of a family of algorithms that are related to differential evolution, where you take sort of many walkers, not just one that's running around, but a whole group, and you take the difference between two to decide which directions you would make the next proposal in. So what that actually does is you pick pairs, you compute the vector between them, and then you draw a new proposal in that direction. That has the very nice property that because your walkers are already distributed near or in that shape that you're trying to explore, that it sort of adapts to the geometry of this space. But it really only works if your correlations are Gaussian. If you have bananas or some complicated shapes, it doesn't work as well. It also has odd properties in higher dimensions, like 20, maybe 50 dimensions. It tends to collapse to a linear subspace, and there's an interesting paper on that. If you want to go to really high dimensions, like hundreds or maybe millions of parameters, you really have no choice but to use Hamiltonian Monte Carlo, which uses gradients to guide where it should sample more often. Yeah, the disadvantage is exactly that. You need for each of your spectral models, not just the likelihood, but the gradient of the likelihood. And that's almost never implemented. So we tend not to use that technique. I would just show you some of these algorithms running around. And there's a very nice website that shows that. Just see if I can bring that up. Okay, so this would be Hamiltonian Monte Carlo. It sort of uses the potential of this posterior to accelerate and decelerate. And you see it can walk quite far. And on the bottom and on the left, you see the visited points, and it makes sort of a histogram that tries to approximate the true distribution. That's that curve and the contours that are shown here. Okay, so let me just switch over to the Gaussian proposal. So here it's proposing, red would be rejections, and green would be accepted points. So it's, sometimes it just stays and it keeps counting those points where it stayed, and yeah, builds up the distribution. You already see that very often it doesn't go anywhere. And I speed that up, you sort of see it building up histograms. Okay, so one drawback of these MCMC techniques is it won't work very well if you have another mode that's far away. So if we switch, for example, to a multimodal distribution here, it will, I mean, here it's sort of, they're close together, but it takes quite a long time for the chain to actually jump to another node. So you can imagine if they're even further apart, it would basically never go there. Okay. So it's a fun tool to play around with, but I should go on. How do you know when your Markov chain has actually reached convergence and represents your posterior? It's very difficult. You can look at plots of, for example, the first coordinate and try to determine how correlated this random walk is, and make sure that you run many lengths of this autocorrelation. There are many diagnostics that try to identify when things have gone wrong, but you cannot prove that things have gone right. That's a bit of an issue. Typically, these Markov chains have first a phase where they try to go from regions of very poor fits to some decent fits. So that's sort of a burn-in or identification of the posterior. It's also another name for it. And then a phase where it sort of walks around in this parameter space. And that can also take a long time to really fully sample this posterior. Okay, so in real life, these parameter spaces are often complex, can have these bananas, can have multiple modes, can have tails that are not falling off like a Gaussian, but have a lot of probability. And they can be high dimensional, 10, 20 parameters. And that makes it quite difficult. At the same time, what we want to do is we want to try out a bunch of models. And we want to do this in a reproducible way, right? That doesn't depend on, or doesn't strongly depend on where you start. And so for Rosita, for example, we also have a very large number of sources, like tens of thousands of sources. So then you need an algorithm that is robust, that you can just let go, and it does reasonable things and explores this parameter space in a global sense. Okay, so those would be nice properties, and I will come back to that later. I will give you some more things we want on how to do model comparison. So we talked about model comparison a little bit, and then later I will tell you how we actually compute this. So for comparing two models, there are many styles of doing model comparison. It depends a bit exactly what question you have in mind and what kind of models you want to compare. So you could be in a scenario where you don't really physically care about what's going on. You just try to approximate the data, maybe to get rid of some features. So let's say you have polynomials or Gaussians, or you just put a black body because you want to put something there, but you don't actually believe this to be a physical model. How do you compare two such models then? Well, one way is to look at how much information is stored in this model. So that's more of an information theory point of view. Another way that's very common in machine learning is to look at some data that has been left out. You give out some data and use this model to predict in that range. And you look at the quality of that prediction. Okay. Another scenario is where you ask, well, is some component present or not? In this case, sometimes, okay, so one question is this statistically significant? Another way of asking the question is, does this component have really a meaningful impact? So for example, you could say, if, let's say, a reflection component has a normalization below this value, it's basically not there, right? So you could define a meaningful threshold where you say, this is equivalent to the model without that component. So that's sort of illustrated here. You define this region of practical equivalence, rho, and you ask, well, is the posterior of your parameter inside that region or outside that region? So that's one way to go about it. And then a third scenario is where Bayesian model comparison can come in. If you have two or more competing well-defined physical models, and you have well-justified priors on these, for example, you know, okay, from previous samples, for example, from theory, you know, okay, the temperatures should be distributed like this. You know, the luminosity should be distributed more or less like this. And so you have, I don't know, completely different models, black body, and let's say pulse or something like that. And then you can do this style of model. So let me just first go to this information criteria. One very popular one is the Ake information criterion. It's actually rooted in quite deep information theory, but the formula looks extremely simple. And that is, you just take the C-star value, or minus 2 times the maximum likelihood, and you punish that by 2 times the number of free parameters. Okay, and you choose the model that has the lowest AIC. So it's nice because it's sort of independent of priors, but a drawback here is that you don't actually have a way to say what's going on if the AICs are very similar to each other. So it's also unclear where to draw these thresholds. Word on the street is that something like 4 to 8 difference is reasonable, significant on the tools. Okay, and so finally, let me talk about this Bayesian model comparison. As I said, you take the integrals of the 2 parameter spaces. You take the ratio of those two. Those would be the base factor. And you have to multiply the base factor by the model target. What does that actually do? So if you consider these average likelihoods over this parameter space, how does that behave? Let's say you have 2 models and you have your data set. Let's say model 2 is inflexible and can only do certain shapes. So you can make these lines. So you can get a sort of okay-ish fit to the data, not very good, but not bad. So your likelihood is gonna have some value, and it's gonna be associated with some region in this parameters. Okay. And then you have another model, which is extremely flexible, can make all kinds of shapes, all kinds of wiggles. So it's gonna be able to perfectly fit these data. Likelihood is gonna be very high. But the region in this parameter space where the likelihood is high is going to be tiny, because as soon as you walk away a little bit, the model shape is going to be completely different because it has to make all these different shapes across the parameter space. So you have high likelihood, but the volume corresponding to that is tiny. So if you compute the integral, if you multiply these two together, this model is being punished for being so flexible. So that's what base factors do. They don't go by number of parameters, but they go by this diversity of predictions that models can make. Okay, so here's the formula. You take the 2 integrals over the 2 parameter spaces, the Bayesian evidence, often abbreviated as Z. You multiply each with its model prior. And then on the left, you get the probability of model 1 being the true model. relative to model 2 being the true model. So that's a very interesting thing that you might want to know. If you not just have 2 models, but multiple models, you can do the same thing. You get the relative probabilities of each model by dividing by the sum of these terms. Okay. How do you actually get these prior odds on these models? It's a little bit difficult. What I would recommend is to not compute that in the results section, but just report the base factors and then sort of leave it to the discussion section to multiply on the reader's preferred model priors. There's another question or confusion that often arises, which is, okay, let's say you have this relative probability of model 1 to model 2 to be, let's say, 3 to 1, okay? Now, you get these relative probabilities, but often or sometimes you want to make a decision. So you want to discard one model and continue working with model 1, let's say. So how often would you make a mistake by picking model 1, although in reality you should have picked model 2? And these false decision rates is not something you get out from Bayesian theory, because in Bayesian reasoning, you never make a decision. You only get relative probabilities. So to find out your false selection rates, you have to do simulations. And that's actually also the case if you do delta C stats, because these terms under which, for example, likelihood ratio tests are valid are not the case in our applications. Our model is not linear. We're not in the high data region. We have to do simulations. Okay, so how do we actually compute these things? Nested sampling is a parameter space exploration algorithm and integration algorithm that looks at the entire parameter space. It produces posterior samples, so you can use constrained parameters. It computes the evidence that you can use to do model comparison. It does not need gradients. That's nice. It is quite efficient, especially if you have slow models, like convolutional models. And it has the nice property that there is a point in this algorithm where it knows it's done. So it converges by itself. And that's probably the thing I like most about it compared to MCMC. Okay, so how does it work? So in MCMC, you are jumping around in this parameter space and you're building up sort of vertical slices of where you visited. Nested sampling works sort of the other way around. So you can represent your posterior by these horizontal slabs, and then the integral is summing up these slabs. And so like a pyramid, for example. And so how do you do this integral? Well, you look at the width of the slab and the height of the slab. And in this case, we keep track of how much the slab shrank when you went up in likelihood. And you sum up how much was taken away, the volume that was shaved off, times the height. And so you can sort of imagine as shells, and each of those shells is then going to be represented by one point. That gives you the posterior samples, and summing up all of these slabs gives you the integral. So we have to sort of figure out how to construct these slabs so that we can sum them up. And if you're more interested in the theory, well, I recently wrote a review paper, which goes a bit on the technical side, but on the mathematical derivations and theorems, maybe have a look at those. Okay, so how does it actually work? Let's go through an example. Let's say you have a two-dimensional parameter space illustrated by this box. You throw in 200 points. They are called life points, similar to walkers. You throw in 200 points. You say this volume, the entire volume. So we say 1 is the size of this volume. And now you evaluate the likelihood of each of those points. Each of those points correspond to a model curve and have a quality of the fit. And so you identify the point with the worst fit, and you take that out. Okay, so you remove one point. Now you have to imagine that the volume represented by the remainder of the points, the volume has shrunk by 1/200, because you took 1/200 out. So now we have a way of knowing how much the volume shrank. And now we're going to put another point in so we don't run out of points. We're going to throw in another point and get uniformly sampled from this parameter space. But we require that it cannot have a worse fit than the point we just took out. Okay, so you remove a point, know its likelihood, throw in a new point, but only accept those that have a better fit than the one we just took out. And you keep iterating this. And what that does is you keeping this population of live points that goes to better and better fits. So it sort of scans up vertically in likelihood. And so later, after many iterations, you end up with a scenario like in the middle left here, where all your points are very, very good fits. And they sample maybe some very small region of this parameter. And you, at each iteration, you keep track of the volume. The volume shrank 1/200 in each iteration, so it geometrically gets smaller. And so as you keep summing up what I said before, as you keep summing up, at some point this volume is going to be so tiny that it doesn't contribute to this integral. All your points are going to have very similar likelihoods in a tiny region of the parameter space, and you're done. Okay? So at that point, this algorithm converges, and you can stop. But I haven't explained how you actually sample a new point from your prior that is a better fit than the point you just took out. And that's sort of the missing ingredient to this framework of nested sampling. And it's sort of similar to what's in MCMC algorithm. You have these transition kernels. In nested sampling, there are also several variants based on how you do this likelihood restricted prior sampling. But the nice thing here is they're actually very general solutions that perform very well over a wide variety of models. And one very popular method to efficiently sample new points was proposed by Monte. And the idea here is that you have some points already, you have your live point, and they already trace out sort of the region where you're going to find the next good point. So Monte clusters these points into ellipsoids and expands these ellipsoids by a fudge factor, and then only samples from this region, so sort of samples from the neighborhood of the existing live points. And that works very well. Another algorithm that I proposed is MLFriends. Very similar idea, just makes ellipsoids around each of those points. And then instead of having a fudge factor, it actually uses something similar to what's used in machine learning. It leaves out some points, makes sure the ellipsoids of the remainder are expanded large enough to recover those left out points. So it automatically finds out the necessary expansion to be safe, to be a safe padding region around this line. So that's one nice thing about this algorithm, that it doesn't actually have any additional parameters. Right, so we can have a look at what that does, or what that looks like. I just want to say MLFriends is the algorithm implemented in Ultranest. Ultranest is a Python general purpose Bayesian fitting package, and it's the package that's used in BXA as well. So let me just bring that up, if I can. Okay, let me just bring up this multimodal thing because I think it's nice. So initially we have points in the entire parameter space, and around each of these blue points, blue light points, there is a region defined, sort of a bubble defined, and it's going to sample from this bubble, and it's replacing always one point. That's the start of the arrows. It's going to replace a point with a new point sampled from this region. And as it goes on, it goes higher and higher in likelihood contours. Those are the circles in the background, the blue ones. As you see that the light points are concentrating more and more to those three Gaussian peaks. And you also see that the region constructed around those, this neighborhood region constructed, is focusing to that neighborhood. And a nice property of this algorithm, as you see here, it doesn't have problems if you have multiple nodes. Just keep scanning up, and the light points trace out where the likelihood threshold is currently being reached. And if we accelerate this a little bit, you see that the region or the volume becomes smaller and smaller. This peak is going to thin out because the likelihood threshold goes above it. Finally, we only have this one left. Region gets smaller and smaller, and at some point, you can stop integrating because it doesn't contribute anymore. And you see at the bottom, you have the posteriors being reconstructed, and that's nice. Okay. Okay, so what can we actually diagnose about this algorithm while it's running? Well, we have the iteration, and that's something, I should have said that, that's something that you will very often see when you run alternest. You get this diagnostic output. So what does that all mean? Just move that away. So first of all, we have the iteration it is in, so how often it removes a point. We have how efficient our method of proposing new points is. So the number of model evaluations that it has tried per number of iterations that it progressed in. So that's shown on the top right here. Iterations by number of model evaluations and the efficiency. The number of live points. You can learn something about where your live points are currently running around, or where they lie. So in alternest, if you use it in Jupyter notebooks or also on the command line, you usually get these plots, which show you where it is currently exploring. And you can look at the likelihoods of those points, which again is related to the C-stats. So that's shown in the middle, well, where it's like equals up here. That's the range of likelihoods that are currently being looked at. Here is where it thinks it wants to stop. And then here is the progress. And that's related to this integral you're integrating. And you ask, well, how much of this integral is already in the points that I have removed? And how much is still in the live points? Because they have high likelihood. They might have a small volume. So you can ask which of those two contains more contribution to the integral. Finally, there's an interesting test to make sure that the algorithm is performing well, which is to ask, okay, you're sampling a new point, and you're going to insert that into the live points. You can ask, well, the likelihood that you sampled, what's the rank among the live points? Where would you insert that if those live points were sorted by likelihood? And you would expect that it's uniformly distributed in rank, but you can check that. And it could happen that it always ends up at the lowest likelihoods for some reason. And then this test would pick that up. So that's another diagnostic that is being printed in alternate. Finally, you don't have to use MLFriends, which especially doesn't work too well if you go to very high dimensions. And in that case, you might want to use actually an MCMC sampler to start from a live point, run around in your parameter space for a number of steps. until you say, okay, I have a new point, and this one is independent of where I started. And a very popular one that's also implemented in Polycard, but also in Ultranest, is to use slice sampling. So for these classes of algorithms, these step samplers that run around in the parameter space, you of course have to define how many steps you walk. How do you decide that? Not so easy. I usually look at the evidence being produced. If you start with one number of steps, 2 steps, 4 steps, 16 steps, you increase it and you see, well, at what point you always get the same results, then you probably have a good number of steps. Okay, so that was nested sampling. What is then BXA? BXA is actually just about 50 lines of code, if you come down to it. And it's just plugging 2 things together. One is a fully fledged fitting environment like Sherpa and PyExpect, which can read or can work with community models, can read data formats that are used. And it plugs that into some sophisticated inference engine based on nested sampling. It used to be multi-nest. Be thankful it's not multi-nest anymore. You would have to install Fortran stuff, and that even also complicated. PyExpect and Sherpa is complicated enough. Now it uses Ultranest, which is a pure Python package. Nice things about both of these actually is that you can resume fit, you can parallelize it on a computing cluster, and it does some checking on whether the fit performed okay. BXA does a little bit more nowadays. You have some background models, you have some visualization tools that are quite limited. You're supposed to do your own visualization most of the time. But that's sort of what it can do, but the implications of this small package are quite interesting. So you can give it any model or any data that's any definition that is supported by your fitting environment, and you give it prior probability distributions, and then it can produce for you posterior probability plots. So where give you posterior constraints, and from that you can, I haven't explained that, you can also make sample distributions, and it can compute the evidence that you can use for model. The nice thing is you don't need a good starting point, doesn't care about that. Samples directly from the entire prior. You don't need a number of minimal counts for this to work. I will show that in a second. And you don't need to rebin your data for example, minimize it to behave well, because it's just a different style of algorithms. So just to illustrate that, here I'm showing a spectrum that I simulated. It has 2 components, sort of a reflection component in green and a nuisance component, power law, in the software energies. And on the right, I will show the constraints on luminosity and column density of this model. And at the same time, I will make the source fainter and fainter. And we will see how the parameter constraints change as that is being output by BXA. Okay, so initially all the parameters are constrained well. Just move that a little bit. Just wait for that to loop. Initially, all the probability distributions represented by the posterior samples are concentrated very narrow around the true value, that's the red spot. But as it gets fainter, these probability distributions expand. There is a point where it's actually bimodal, where there are 2 solutions. And at some point, you basically have nothing left. You have very few counts, but you can still apply this procedure, and you still get information out, namely that this cannot be a luminous, unobscured source. So that region bottom right of this parameter space is excluded, even if you have 0 counts. You can run BXA with 0 counts. Okay. Yeah, so that gives you the probability distributions. There's some bells and whistles on BXA that we will try out. Background models for a variety of instruments, some helper scripts, yeah, things like that. Yeah, so briefly, I mentioned that you shouldn't use base factors directly for delta C stats for making decisions about models if you want to know how often you would be wrong. So how do you find out whether you will make a wrong decision when you say, okay, I accept the model with the higher delta C stat or something like that? Well, the workflow is this. You simulate data under the simpler model. So let's say you simulate 100 spectra under the simpler model, and then you fit each of those data sets with both the simpler and the more complex model, and you look at the base factor, for example, or the delta C stat. In this case, it's the base factor. And you ask, well, what's the distribution of base factors I get, even though I assumed the simpler model? And that's shown in the red here. That's the distribution of base factors for one particular model that I get. And then you can look, well, where's, for example, the 99.9% quantile? And you say, well, if I get a base factor in my real data above that, that happens rarely by chance, in 0.1% of cases. So then you look at the real data and compute a base factor. Let's say it's 100, and then you can confidently say, okay, I accept this because I have a false decision rate of less than 0.1%. So there are several advantages to going about it like this. You get rid of the dependence of model priors, because that's just the scaling along the x-axis that's being calibrated out. You still operate within a Bayesian framework where this base factor has a meaning, but you get additionally frequentist properties on it, on your decision, how often you would be wrong about applying a cut. The disadvantages, this is computationally expensive, but with nested sampling and BXA, you can actually do this. Yeah, this I already described how I recommend to do model comparison. Depends what scenario you are in. You can look at this later. Here's some final practical advice. So you don't have to use BXA. You don't have to use PyXspec or Sherpa. There are other packages as well. You can do good Bayesian inference with other packages. Some packages make it harder than others. That's all I want to say. It's also important in papers to state exactly what you're doing so that people can understand and maybe judge what they would have done differently and how much that would have affected things. I would say always use CSTAT. The reasons to use Gaussian statistics used to be computational and they're not really valid anymore. You can always use Poisson. Not everything has to be a test. You can visualize, and that's actually what's, if you talk to statisticians, that's what they recommend. Do a lot of visualizations. For example, to judge how models are good or not. Also helps to think sometimes. It's good practice to vary your priors and your model assumptions. So try out different scenarios and see how that affects things. It's very important. And make simulations, generate data sets, and apply your workflow and see how it behaves. That's sort of annoying, it takes time, but it raises your confidence in what you do. There are forums to ask for help. So there's, for example, the Astrostatistics Facebook group is quite active for newcomers to ask basic questions or more advanced questions about how things work, or what someone would do, and we're happy to help out. Also the XSpec group, which is not necessarily limited to XSpec anymore. People also ask general questions about X-ray spectral analysis. Or, you can always open GitHub issues on BXA or email me if you need help. So BXA, the idea is to do robust inference within environments you're already familiar with. The idea for it is that it's open source and community developed, so you're very welcome to contribute to it, to report bugs, to add visualizations, for example. And you can build on top of it. You can build pipelines based on it and maybe makes your own turnkey tool that you apply to your favorite class of objects. For example, I made, for example, a tool that can fit obscured ATM. And you just run it on the files you already have. You don't have to do much. You could, for example, make a tool that helps you write proposals. And finally, okay, I didn't have time for that, but I think one underappreciated idea in X-ray astronomy is to leave some data out. Don't fit it, and see how your model behaves on that data. So that's just a food for thought, and I think I'll stop here.
Okay, thanks very much, Johannes. Do we have any questions first in the hall?
Right. So I don't know if people online understood, but I would just repeat the question. So in this case, where you try to calibrate model decisions, when you construct these distributions, you're assuming that one model is the correct one, and whether that's a problem similar to confidence intervals, which also assumes that one model is correct. So in this case, you sort of have a default standpoint where your state of information is you are at the simple model, and you ask whether you should make the step to an alternative model. That's the framework. This is null hypothesis significance testing. Basic frequentists making a test. And yes, it is true that you're assuming here. So basically what you're asking is, how often would I make the how often would I make the step wrongly? So if you start in A, how often would I, by mistake, still make the step to B? And of course, you can ask the other question as well. Like, you can simulate on the other model and ask, how often did I not make the step, although I should have? And that would be the false negative rate. And both are interesting. I here only showed the false positive rate, but you can do both. You don't have to rely on one model. And yeah, this gets a little bit complicated if you have 10 models and you have to simulate them all and fit all of them together. But basically, yeah, that's the idea, that you characterize your workflow of jumping from one model to the other.
I have one more comment. Yeah, it's still the same, but yeah, I saw earlier in the early slides that you were talking about the 3 ml.
Yes, yeah. Where did I say that? Here. Right. Yeah. Yes. Yeah, so that hasn't been mentioned yesterday, but there's another a bit younger fitting package called 3ml. And that the team around that tries to work in particular on multi-mission fitting, so combine X-rays with optical and neutrinos and I don't know, some particle experiments. So then you can fit all of these likelihoods together. That's their concept. And so the reason it's in gray is because this is not done by DXA itself, but they have included, so they can use several algorithms, and one of them is alternate. All I wanted to say is you can do this analysis, same thing basically, also with 3 node. And I think Specs also has an alternate link now.
Okay, so Martin Speaker on the chat was asking, so when you start to find constancy, he was asking, explain the meaning of the -1 and the definition of the constancy. And if it's related to
Yeah. Okay. Yeah, I always get confused about this. If it's -1 in C-stat or log likelihood, so don't nail me down on that. But basically the assumption is, if your likelihood behaves like a Gaussian, then you know that in a Gaussian, if you walk 1 sigma away, your log likelihood decreases by a certain factor. And that 1 sigma contains 68% of the probability, right? So applying this to find the 68% region, you walk down corresponding to that in a Gaussian. So it might be off by a factor of 2 or something, but that's the idea.
Then we had one other question from the same person, just asking if you take the sampling one more time, especially with the part about losing.
Yeah. Yeah, don't worry if you don't understand this the first time. It also took me a long time to really understand this sampling. And there are several kinds of understanding the algorithm, and maybe listen to a few, and maybe you like one more than the other. But so what happens when you remove a point, that point has a coordinate and a likelihood. And you use that point to represent the shell of likelihood ranges in this iteration that you've just excluded. So in the next iteration, you will never look at this region again. So you're using this point to represent one of these slabs or one of these shells that are being sliced off. And so these dead points, removing this dead point, you put it on a pile of posterior points that you will use. And each of those points have then a weight. And the weight is this volume shrinkage, which is 1/200 times the volume of your current iteration. You are keeping track of the volume times the likelihood. Okay, so you have each dead point is associated with the weight. And so you have, in the end, you've done, I don't know, 10,000 iterations, you get 10,000 points. Each of them have a weight and a coordinate. And now with these posterior points, it's not so convenient to carry these weights around. So what Ultranest or Multinest does is it resamples those proportional to the weights to give you a sample of points that are equally probable. Just you resampling using the weights. So that's how you actually get the posteriors from nested sampling. Does that help, or is there a follow-up question?
Yeah, so we're a little late breaking up for lunch. One more. So then if there are any sources for beginners from those who understand the code step by step,
Mhm.
then you can share on the Slack.
Yeah, sure. For nested sampling, I guess.
Oh yeah, I will see that.
Yeah. I recently gave a block course on Monte Carlo algorithms like MCMC and nested sampling, and there's a whole block on implementing nested sampling from scratch, if you're interested in that. And that's on my YouTube channel. I will put a link in the Slack if you really want to understand the algorithm in detail.
The link to all those lectures are also on the YouTube.
Okay. So yeah, we're done for this morning. So let's thank Johannes again. And the Zoom still on.